So, we have been discussing so far the steady state analysis of mass transfer and biochemical reaction in immobilized enzyme reactors, and as we have discussed yesterday about the external film diffusion, that is in cases where we consider non-porous matrices under steady state condition, the rate of mass transfer can be equated to that of rate of biochemical reaction, and then by a step by analysis one can come under two extreme conditions. One, under high substrate concentration we get a Lineweaver profile which is analogous to ordinary soluble enzyme kinetics, sorry the other way, this one. And in the case of low substrate concentration, that is in this case low substrate concentration, high substrate concentration, you get a difference in slope, and the measurement of slope at two distinct stages of Lineweaver plot gives you a estimate of the value of mass transfer coefficient due to film diffusion. KL AM can be computed, and therefore, based on the observed reaction velocity in the case of a immobilized enzyme reactor, one can determine the value of SB minus SS, that is the substrate concentration gradient, and the magnitude of this determines whether the reaction is diffusion limited or otherwise. If I mean the SB minus SS is 0 essentially or a very small quantity, then there is no diffusion limitation. If this magnitude is large or SB is much larger than SS, in that case diffusion, the film diffusion is the dominant player. And so, the nature of Lineweaver plot under the range of condition of substrate concentration can give you an idea of the mass transfer coefficient. Another approach now, so basically what we are now looking at, a general approach to understand the external film diffusion is that we determine by some experimental method or an analytical method or an empirical equation the magnitude of the mass transfer coefficient, and the magnitude of mass transfer coefficient will give you the magnitude of the concentration gradient. And so, another alternative route to estimation of mass transfer coefficient has been on the basis of some empirical relationship, what we call as JD factor. Now, a JD factor has been defined in the case of heterogeneous catalysis in chemical engineering in general, and of course, which applies very well to even enzyme catalyzed reactions, and JD factor is defined as a lumped parameter which takes into account the mass transfer coefficient, particularly film diffusion coefficient, as well as the reactor operational parameters. The JD factor is your KL rho upon G into mu upon rho D to the power 2 by 3. Now, this essentially is the Schmidt number. So, basically the first term in the parenthesis represents the mass transfer function, the other is a dimensional number which gives you the operational parameters, and here KL is the mass transfer coefficient, rho is the density, G is the superficial mass velocity, and mu is the viscosity, rho is again density, and D is the diffusivity. And this lumped parameter has been shown at least empirically in a large number of experimental data. It has been noted that your JD is equal to C Reynolds number to the power minus n. Now, of course, a very general relationship for JD factor has been given, that it is a function of Reynolds number to the power minus n, and of course, under different conditions of particle shape and in the range of Reynolds number, the magnitude of C and n varies, and that can be estimated for a particular system. And of course, a large number of correlations of giving the values of C and n have been proposed under different conditions, and one of them which meets the actual reaction conditions can be chosen from the literature and used for estimation of JD. Okay. Now, if you look at this one, now you will notice that your from the estimation of JD factor as a function of C Reynolds number to the power minus n, one can determine the value of KL. Now, because your KL will be equal to J d into G upon rho Schmidt number to the power 2 by 3. I mean, if you just convert this, your K L, magnitude of K L is related to the J d factor by the J d value and also a combination of the reactor operational parameters, superficial mass velocity, density and Schmidt number, and the magnitude of then K L gives you the at steady state the reaction rate, that is your K L A m S b minus S s, that is your R m. The rate of mass transfer under steady state, both the reaction the biochemical reaction and the mass transfer rate are equal, and therefore, one can get from the magnitude of K L A m, one can get the, and now this V can be considered as the observed reaction rate, which has been monitored experimentally, and therefore, one can determine the magnitude of S p minus S s, and that determines whether the diffusional control is there or not, and accordingly one can design the reactor. Now, J d can be computed from a variety of correlations, as I mentioned. One of them which has been applied, developed by McCune and Wilhelm. Of course, this is only one of probably a large number of relationships that are reported in the literature of heterogeneous catalysis in chemical engineering, which gives your, for spherical particle, J d is equal to 1.625 NRE to the power minus 507. Of course, this is just a, I mean, sort of one of the, one of the parameter, one of the relationship which has been proposed, but a large number of such empirical correlations are known. Now, once the magnitude of K L is known, then one can really incorporate the value of K L into the rate constants of a reactor performance equation. Now, if you look for in the practical, in most of the practical cases, whether it is a plug flow reactor or a CSTR, the error involved in assuming the whole reaction to be under a first order regime or a zero order regime is not very large, depending on the initial substrate concentration. For example, in the case of a CSTR, of course, the life is much simpler. If the fractional conversion desired is very high, then even if at a high substrate concentration, initial substrate concentration, the reaction the substrate concentration in the reactor will be quite low, and that is at the substrate concentration which is going in the outlet stream. So, a first order approximation is not something which is invalid, and as I mentioned earlier, if you take certain data, roughly an error of about 10% in calculation of the space velocity is encountered. Similarly, in the case of PFR, a large fraction of the reactor, because the enzyme loading is very high usually in PFR, therefore, a large fraction of the PFR also experiences a low substrate concentration. Of course, it also experiences product concentration, high product concentration, but substrate concentration keeps reducing, and towards the end of the reactor, the substrate concentration will be very low, and one can assume a first order kinetics. Now, if you consider let us say first order case, then the reaction velocity will be your Kf Am into Ss. Now, mind it that Kf I have defined here as a pseudo first order rate constant, which is based on surface area, not volumetric rate constant, but a surface area based rate constant, and just to have a dimensional homogeneity with the mass transfer correlation. And your here Kf is essentially equal to a pseudo first order rate constant for an enzyme catalyzed reaction as K2 E naught upon K dash m, and therefore, your rate of mass transfer and your rate of mass transfer is KL Am into Sb minus Ss. Now, in the case of a non-porous particle, the issue is essentially to develop an expression which gives you the substrate concentration at the surface, because the reaction will take place at the surface of substrate concentration. If you equate the two, that is your B dash is equal to Rm, and that will imply that your Kf Am into Ss is equal to Kl Am Sb minus Ss, and therefore, from this the substrate concentration of the surface can be calculated as Kl into Sb upon Kf plus Kl, or the rate observed rate is your Kl Kf Am into Sb upon Kf plus Kl. Now, essentially then what you notice is that the actual rate constant, which incorporates the film diffusion coefficient also, is essentially this parameter, or rather Am you can delete this parameter, that is your Km apparent will be your Kf Kl into Am upon Kf plus Kl. So, essentially in your reactor design equation, if you incorporate instead of a first order rate constant as this one, which is based on only on biochemical reaction, if you incorporate this rate expression, this value, and of course, as I mentioned, Kl can be determined either from your experimental data, from the Lineweaver plot, or from your empirical equation of Jd factor. One can determine Kl. Am is again an experimental based on the geometry of the particle, and then Kf apparent can be determined, and Kf apparent can be used to designate the reactor performance of the first order immobilized enzyme reactor with film diffusion limitations or film diffusion control. Another way, again an empirical way to look at the film diffusion, has been proposed by Satterfield. I must here again point out that the whole analysis of the immobilized enzyme reactor has been largely dominated by chemical engineering literature, particularly with reference to heterogeneous catalysis, because the systems are very identical excepting the thermal stability, specificity, which are attributed to enzymatic reactions, but the catalysis part, whether it is a heterogeneous catalyst in the case of chemical engineering, that means a catalyst supported on a solid matrix. Even in the chemical engineering, that is a very conventional thing, only the difference is that those catalysts are very stable in terms of their thermal, operational as well as storage stability, whereas our immobilized enzymes are not as stable as the chemical, but again all the analysis is identical, and of course Satterfield also provided a single point reactor performance equation based on film diffusion control for a heterogeneous catalyst, and he defined a parameter Z as equal to epsilon NRE to the power 2 by 3 and to the Schmidt number to the power 2 by 3 upon 1.09 AV ln y1 upon y2. Now, here sigma is essentially our y days, as we are familiar, Reynolds number, and this is Schmidt number, and AV essentially is the ratio of particle surface area to reactor volume, particle surface area to reactor volume, and y1 is the mole fraction of substrate in feet, y2 is equal to mole fraction of substrate in the product stream, and basically Z essentially is the length of or the height of packed bed required for mass transfer. That means Z is the height of the length of the packed bed required to transfer the substrate concentration across the film, and as a function of Reynolds number and Schmidt number. So, basically and purely on the basis of mass transfer control, no biochemical reaction is assumed here. that as if the mass transfer has to be incorporated, this much of length of the reactor is required under these operational conditions to have the substrate concentration reach equivalent to bulk. That means, to make Sb minus Ss equal to 0 without any biochemical reaction, this much of length of the height of the reactor is required under these operational conditions. Now, so obviously, based on the operational data, that means the concentration of substrate in the product, substrate in the feed and the product stream, as well as the parameters of the reactor operation and the particle morphology, the particle size, one can determine the length of the reactor required, and if this length of the reactor required is relatively to the length of the reactor required for biochemical reaction. Now, you see, you compare this height required to that of the height required, let us say this is Z1, if you require the Z2 based on biochemical reaction, if you just calculate idealized reactor performance equation and calculate the height of the reactor required and compare the two values, that gives you an identification whether film diffusion is controlling or not. And essentially, the one which is larger has to be used. So, for example, let us say if this Z is much smaller than the height required for biochemical reaction, then you do not have to worry about diffusion. You simply design your reactor on the basis of biochemical reaction and be happy. On the other hand, if this height required is reasonably high, then you forget about biochemical reaction and design the reactor based on diffusional requirements, based on the mass transfer coefficient.
The length of that reactor will be equal to this?
This is the height of the reactor. Of course, this is basically a empirical equation, but depending upon the reactor operation data, the height required for effecting the mass transfer across the field.
That is fine, but suppose this Z1 is much greater than Z2, and then we are supposed to design a reactor based on diffusion limitations.
Right, only Z1, you do not bother about Z2.
So then will the length of the reactor be equal to Z1?
Z1, right. You do not have to then bother about the biochemical reaction, because in that height reaction would have already, would have been possible to take place.
So, but in this case the reaction will take place only at the top point where
Yes.
it has finally reached.
Exactly, what we are saying, we are assuming here that there is no reaction within the pores of the particle, all the enzyme is present on the surface, and in the thin film there is no reaction taking place. You see, you must appreciate the difference between internal pore diffusion and external film diffusion. While in the case of internal pore diffusion, across during the transport of the substrate in the particle, reaction is also taking place, whereas here there is no reaction taking place along with the mass transfer. It is only mass transfer. Only difference is that between the bulk and the surface where the reaction is taking place, there is a concentration gradient, and ideally if the diffusion control has to be out of picture, in that case the concentration gradient should not be large, and this concentration can be eased if assuming that there is no substrate consumption at the surface. You see, normally what is happening, that the substrate is getting transported from bulk to the surface, and at the surface reaction is taking place, and if suppose there is no reaction taking place, then along the length of the reactor at Z, the substrate concentration will reach to Sb, same as in bulk. It will take some time, but whereas if the biochemical reaction is also taking place at substrate, then that length required will be given by Z2 at substrate concentration Ss. Now, one of the two which is larger is required to be considered. So, this is what we were talking about, the external film diffusion, and the other part of the whole story of the steady state analysis is related to internal pore diffusion. As I mentioned earlier, that in the case of porous matrices, now we are talking of porous matrices, a very large quantity or fraction of the total enzyme which is immobilized is within the pores of the particle. The quantity of enzyme immobilized on the surface is practically in fact very small compared to the total surface area in which the whole enzyme is distributed inside the inside the pores of the reactor. And therefore, it becomes very important that we look at the concentration of substrate available for the enzymatic reaction within the pores of the reaction. Now, very broadly the effect of internal pore diffusion in a very simplistic way is described for isothermal reaction incorporating the pore diffusional effects by a V dash equal to eta K2 dash E naught into SS upon K dash M plus SS. Mind it, I am talking only the again you will notice that I mentioned SS, that means I am excluding the film diffusion. Whatever concentration of substrate has reached at the surface, from there to the pores of the particle we are considering. So, in this case we are not talking about we will consider the case where both the parameters are taken, or rather all the three biochemical reaction, external film diffusion and internal pore diffusion are taken place, but at the moment we are talking only of biochemical reaction and internal pore diffusion, assuming that the film transport through the film is fast enough, which does not create any problem. That means there is no concentration gradient across the film. Now, in this case this is defined by a factor eta, which is called as effectiveness factor. Now, this effectiveness factor essentially is the ratio of the rate of actual reaction in the matrix divided by the maximum reaction rate obtainable if there was no pore diffusional resistance. That means basically what we are trying to say, if I mean a very physical conceptual picture of effectiveness factor can be considered, that is, you for example you take a particle, let us say of 1 millimeter diameter, determine the reaction rate, and then also take a particle, let us say of 10 microns or 20 microns diameter, in which assume that the pore length is very small. The pore length is very small, and I mean even if the diffusional rate is very slow, the substrate can reach to all parts of the enzyme, go down to as low as possible, and the ratio of the two, that means the maximum reaction rate which you can get when you go down in the particle size to that of the reaction rate which is obtained by a particular particle size is defined as the effectiveness factor. And essentially, and you will notice the effectiveness factor is achieved. Now, if you consider for example, let us say if you consider a very hypothetical condition, a single pore as a part of the a matrix. Now, essentially what happens, and this is the surface, let us say. Now, what happens essentially, you are at, this is your, let us say, thin film, you have SB here, you reach SS, there is no substrate concentration gradient, but then here onwards there is a gradient, because now here there are two things we must appreciate in in contrast to the film diffusion limit effects, that one is that there is a rate of diffusion which will also take the substrate will take some time to reach to the different sites of the enzyme present in the pores. The other is the substrate is also getting consumed during the reaction. So, therefore, if suppose the bulk substrate concentration is itself very low, there is likelihood that by the time the substrate reaches to the inside pore center of the particle, there is no substrate present and reaction cannot take place even if enzyme is there. And ultimately, when you will measure the enzyme activity, what you will measure, that the enzyme activity is low, because a part of per unit enzyme loading, the activity which will be expressed by the immovable enzyme particle will be lower. So, therefore, if the particle size is reduced, you get an advantage that the fraction of the total particle which is receiving substrate increases, coming to 1 when the particle size is too small. And usually in most cases, as per the experimental experiences, that a particle size about 30 microns in most cases of the biochemical reactions has been considered to give you an effectiveness factor of 1. Essentially you will see from this relationship that maximum effectiveness factor can be 1 maximum, because that means you have an enzyme reaction rate under the conditions when the whole enzyme particle is flooded with the substrate, the same substrate concentration what is present at surface is present across the particle at all surface, at all the pores, and under that condition the effectiveness factor will be 1. That is what is the sort of ultimate limit, and we normally the internal pore diffusion effects are described by effectiveness factor. Now, I think there is a very tricky situation. In many cases people have also reported effectiveness factor exceeding unity, experimental observations, that you measure the enzyme activity let us say for example for different particle size in a reactor, and the effectiveness factor works out to be more than 1. Under what conditions the effectiveness factor should be more than 1? The first condition, as you will notice as we discussed earlier, will be the enzyme kinetics where substrate inhibition is very strong. The enzymes that are very strongly substrate inhibited may show a effectiveness factor greater than 1, because the reaction rate when the substrate concentration drops becomes higher than at the surface. If the substrate concentration is high at the surface, the reaction rate is low. When the concentration goes down, the reaction rate increases, and therefore the effectiveness factor is 1. The other alternative case of the effectiveness factor exceeding unity is that of a case where we experience partitioning effects, particularly say for example pH. If suppose the product of the reaction provides you a change in the microenvironment, let us say hydrogen ions are produced. Take a typical example of an alcohol dehydrogenase. When the reaction product ends up in hydrogen ions, there will be a pH change, and if that pH change enhances the enzyme activity, then also we will notice the effectiveness factor to be greater than 1. So, there are two cases, extreme cases, where effectiveness factor shows a sort of a discrepancy from the theoretical understanding, which should be equal to.
Can you once again explain the effect of substrate inhibition?
In the case of strongly substrate inhibited enzymes, if the concentration of substrate at the surface is high, which means that for a substrate inhibited reaction the reaction rate will be low, and when because of pore diffusional parameter, the substrate concentration across the pores is reducing. As we saw here, the substrate concentration goes down along the pores, and obviously the substrate concentration going down means the rate of reaction increases, and when you take the whole particle in account, then the bulk of the particle is experiencing lower substrate concentration, means higher reaction velocity, and so therefore this ratio will become more than 1. Or in other words, if you take let us say two particles, one of larger diameter, other is smaller diameter, the reaction rate in the larger particle may be more than the smaller particle. That is what it means by effectiveness factor being 1, and in many cases of substrate inhibited systems, this is a usual pattern which is noticed.
So, if hydrogen ions are produced and the pH change enhances enzyme activity, then the effectiveness factor should be less than 1, not greater than 1.
No, when there is a partitioning of let us say hydrogen ions, and the conditions are such that the rate of reaction as a result of partitioning increases, that is the condition. If the rate of reaction decreases, if the partitioning creates unfavorable conditions for the reaction, then it will not be more than 1. Only when the hydrogen ions are produced and the microenvironment created by the reaction in the form of product.
So how do we compare with co-diffusion and without co-diffusion? Where it is the actual reaction is not restricted by co-diffusion, there also hydrogen ions are being produced, even otherwise they are being produced.
Right.
So how do we compare between the two?
No, in that case, the comparison will be only in the case when the same reaction. That means when you take the same reaction and in your reactor performance equation, in addition to internal pore diffusion, you also consider partitioning effects. Then you cannot really compare the two only by steady state analysis of mass transfer and biochemical reaction. You must incorporate partitioning effects also in the steady state analysis, then only you can compare. At the moment we are talking only of mass transfer and biochemical reaction. Partitioning also can be incorporated, and which can give you the real performance in the case of. And so now basically in the case of internal pore diffusion, a steady state analysis can be made in a simplistic way. We consider a pore, let us say, to be a single cylindrical catalyst pore. Let us say we assume in a very simplistic way that the enzyme is taking place in a cylindrical pore, and now consider a small differential element in this pore, and along which the mass balance can be made. Let us say this is your SS, the substrate concentration at the surface, and this goes down across the pore. Let us say this is your dx, the length of differential element is your dx, and now if you make a mass balance across this differential element at a steady state, you see the output of the substrate will be minus pi r square. Now this is r is your the radius of the pore, pi r square d into ds over dx. Of course this ds over dx is negative, and that is therefore this is essentially your output of the substrate from the pore, minus input, that is your plus pi r square d into ds over dx. Sorry, this can be out. Input plus the conversion as a result of the biochemical reaction, that is your V into or V dash into 2 pi r into dx. Now this should be equal to 0. As at steady state we make a mass balance for substrate across the differential element, we get this. Now mind it, I think I must again here remind one thing, that this reaction velocity is based on surface area and not volumetric reaction velocity, as we are usually used to in the case of soluble enzymes.
This is
Now,
V dash is
V dash is based on surface area. Unlike in the case of soluble enzyme, where we usually represent in the volumetric, and that's why we have multiplied by 2 pi r the. And now if you rearrange, you get ds over dx out minus ds over dx in upon dx minus 2 over r into d, sorry r capital, r into d into v dash equal to 0. Now if you take limit, let it like dx tend to 0, you can write simply as a second order differential equation, d2s over dx square minus 2 by d into r equal into v dash equal to 0. Now this gives you a generalized second order differential equation which can be set for internal pore diffusion cum biochemical reaction. Now here of course you can also make modification. If this reaction velocity you transfer in the volumetric form, like for example k into v is equal to ks into s. Now let us say these are the two rate constants, it could be 0 order or first order based on volumetric and based on the surface area, and in that case for a cylindrical pore the k will be equal to ks into s upon v, and that is equal to your 2 ks upon r. So therefore one can write here as d2s over dx square minus b dash equal to 0 as the basic second order differential equation, which can give you a solution of which can give you, if you substitute the reaction rate term here depending on the nature of the reaction, either by assuming a first order kinetics or a zero order kinetics or even a Michaelis-Menten kinetics, and of course Michaelis-Menten kinetics will require a numerical solution, analytical solution may be difficult, and you can get the solution of the substrate concentration as a function of the distance x from the surface. Basically, a solution of this will give you this substrate concentration profile in the pore, and of course or inside the particle, and therefore which can give now in most cases.
So how did we arrive at this last step, sir? Where did the diffusion coefficient go?
No, sorry, and
Here the diffusion coefficient.
no, sorry, diffusion coefficient will come here. It is not going right. We are multiplied here too, or V upon D either way. So I mean this can be written for a variety of cases and solved within sort of limits, boundary conditions, so as to give you the reactor performance. I think we will now stop at this point.